In today's lecture, we're going to talk about an important property of CTFT and basically of all the transforms we've seen so far, which is convolution. So the main objectives that we will cover today is we will talk about convolution, the convolution property, and then work some examples. So first I want to start by talking about the convolution and the multiplication properties, and then I will focus on convolution, and the next lecture will be on multiplication. So the convolution property is basically one of the most important properties that you're going to see and encounter in this course, and this is one of the things that you learn in this course that you're going to keep with you probably the rest of your life if you're going to be an engineer. And you've seen this before. So in the time domain, if you have an LTI system here, so an LTI system in the time domain with impulse response h of t and an input x of t, then the output y of t is given as the convolution of the input with the impulse response. So that's the main message here. So the output of the LTI, y of t, is the convolution of the input with the impulse response. Now, this may seem a little bit, as it is called, convoluted. This is why it's just easier to deal with this in the frequency domain. In the frequency domain, convolution becomes a multiplication. So the output, the CTFT of the output is equal to the CTFT of the input times the frequency response of the filter or of the LTI system. So this is an LTI system. So this is basically the convolution property related to LTI systems. So a convolution in the time domain becomes multiplication in the frequency domain. Now, since we talked about duality in the previous lecture, so what is the dual property here? The dual property is the multiplication property that says that multiplication in time domain is the convolution in frequency domain, with one caveat, is that you have here a factor 1 over 2 pi. So multiplication in the time domain is going to be equal to 1 over 2 pi convolution in the frequency domain. The 1 over 2 pi is basically because we have preferred to use omega as the as our variable as our frequency instead of f. So don't forget this factor of 1 over 2 pi. Now you may think, oh, why do I care about multiplication in the time domain? Well, we just saw an example in the previous lecture where you want to do modulation by the carrier frequency to shift the frequency of your signal, which is whether it's an audio or video, to shift it to a frequency that you can transmit that is maybe dictated by the standards such as your TV if you're receiving cable, or you're receiving wireless video, wireless 3G or 4G or any wireless system. So you need to shift this frequency or the spectrum of your signal to fit in that frequency bands. And actually these frequency bands are very, very expensive. So you can look up news about companies buying these frequency bands from, I think, the government or the FCC. But anyways, the multiplication property is also important and also arises a lot, especially in communication, whereas the convolution maybe you will see it a lot more in signal processing. So, and these two properties are summarized in these two graphs. So multiplication is equivalent to convolution in the time domain, and again you have the factor 1 over 2 pi that is important, and do not forget it. So in this slides, for those of you who are more inclined to theory and would love to know why convolution in time domain becomes frequency, I provide a proof here. You can find, it's a standard proof. I don't want to go into it. It's just mainly manipulating integrals. I think the power of this property is how to apply it and how to always remember it and keep it in mind, and to build your intuition around it of how systems work, more than the proof, although the proof is also interesting. And I'll walk through many examples in this lecture to help you show you how to use this property and how to build some engineering intuition around it. So I will highlight the application of the convolution property for these for continuous time signals through a running example. So here we have a low-pass filter with the following impulse response. So you already know that the low-pass filter, the impulse response of it is a sinc function, so it must look something like this. H of t is equal to sine bt divided by pi t, where the frequencies that are allowed to pass through the filter are between the frequencies between minus b and plus b. Actually here there is a typo, it should be 200 pi, and I'll fix it later. So here, this is how this filter looks like. So this is the impulse response of the filter, 200 pi and plus 200 pi. And the goal is to find the output y of t for each one of these input functions here. So each one of these input is basically designed to maybe highlight one idea or one intuition. And I will want to work out these examples, these different examples in the next few slides. So like I mentioned, in the frequency domain, the CTFT of x of t is a low-pass filter that makes the frequencies between, that allows frequency between minus 200 and plus 200 go through. So as I mentioned, in the frequency domain, the low-pass filter has the following frequency response that allows all frequencies between minus 200 pi and plus 200 pi to go through the system, and with gain 1 here, and everything outside this interval is gonna get killed. And why is that? Because remember that in the frequency domain, in the output, we're multiplying it by this spectrum. So we're multiplying by 0 everything that is here and everything that is below minus 200, less than minus 200 pi and above 200 pi. Now, just a quick remark: if you're trying to if you're wondering in hertz, what are the frequencies that are being that are allowed by this filter? So recall that f is equal to omega divided by 2 pi. So in hertz, this is gonna be equal to 100 hertz, and this is equal negative 100 hertz. Not that this is really important here, but I thought it's just good to remind you of this kind of fact. So let us start with the first problem. The first problem is the input here is this x of t, which is 100 pi t divided by pi t. Now immediately you can see that on the frequency domain, this signal is also a box function between minus 100 and plus 100 here, right? Now, where you're gonna try to find the output, so the output is gonna be the product with the filter, and the filter is between minus 100 and plus 100, so it's gonna be minus 200 and plus 200 pi. And the gain is 1 also. So when you multiply the red thing with the green thing, you get the green thing, right? So you're gonna get this thing here between minus 100 pi and plus 100 pi. So in some sense, you could easily see it. So this is basically y of j omega, which is x of j omega times h of j omega. So you can easily see that your signal, your input, has frequencies between minus 100 pi and plus 100 pi, which are within the allowed frequencies by the low-pass filter. So the whole signal is going to go through with no problem, and the output is equal to the input. So this is the first example. The second example is x of t is equal to 2 cosine 800 pi t, and from what we did before, we know that these two cosine are gonna be equivalent to two impulse or two delta function, one at 800 pi, and the other one is at minus 800 pi. And again, and recall that the cosine omega t in the frequency domain is going to lead to two frequency responses, or let's call it omega 0, one at omega 0 and one at negative omega 0. And the gain here and the amplitude or the magnitude is actually pi. Sorry, it's not 2 pi, it's pi. But here we have a factor 2, and this is why we have 2 pi here and 2 pi here. Now, again, I use this example as maybe an excuse to remind you of the CTFT of a cosine. But you should immediately see that this signal has high frequency, which is 800 pi, high with respect to what the low-pass filter let go through. So all this signal, nothing of this signal is going to go through the filter, and the output is going to be 0. Because the filter, if you want to draw the filter here, so the filter is somewhere here, right? And everything outside is 0. Now you probably see what's going on. X of t is 5 sine 300 pi t plus 2 cosine 100 pi t. So this signal has two frequencies in it, one that is 100 frequency and one that is 300. And what the filter is going to do is going to keep the 100 and kill the 300. So, and if you want to do it pictorially, so the filter is here basically. And then it's gonna kill, like I said, so it's gonna kill the 300 and keep the 100. So the output is going to be 2 cosine 100t because it's going to get rid of the 5 sine 300 pi t. Now the fourth question is about x of t equal to e minus 2t u of t. So this is here, and the spectrum is a continuous spectrum, and it's actually complex, and we did this the first lecture. So x of j omega is 1 over 2 plus j omega. So what the output of the filter is going to keep this exactly the same because the gain is 1 in the interval between minus 200 pi and plus 200 pi, and outside is going to be 0. So if you remember, it was something, at least if I want to draw the magnitude here, so I mean if I'm remembering correctly, so the magnitude maybe looks something like this, because when omega goes to infinity, this should go to 0, right? So this is x of, this is the magnitude of x of j omega, and then when you multiply it by the fifth, so the output of the, so the output y of j omega, at least the magnitude of it is going to be something like this. So here, and everything else is going to get killed here. So, and it's going to get killed here because all higher frequencies are going to be set to 0. So these frequencies here are going to be, the filter is going to set to 0. The last example I want to do is a sum of complex exponentials, which is sum over k of ak ejk 70 pi t. Now, if you recall from what we studied maybe in the second lecture, we recall that in the frequency domain, the complex function, so ej omega 0t, and the frequency domain is going to be equal to 2 pi delta omega minus omega 0. So which makes sense because you think of it, ej omega 0t is a cosine plus j sine, so these are one frequency at omega 0, so that's why you're going to get a frequency at omega 0, right? But you have here 2 pi. The 2 pi is just a kind of a result of the unit, which is the omega. It's not too important, but you should not forget about it. So now when I know that the CTFT is linear. So the CTFT of x of t, so x of j omega, is going to be a train of pulses at these multiple of 70 pi, right? So it's gonna be, and the 2 pi here is the same one here. So it's gonna be something like this. So you're gonna have a pulse at k equal to 0 is a pulse at an impulse function at 0, and then k equal to 1 is an impulse function at 70 pi, at 140 pi, and then at 210 pi, and so on and so forth. So again, the interval is 70 pi. And also on the other side here, so you're going to have minus 70, minus 140, minus 210, pi. And again, and the amplitude or the magnitude here is 2 pi. Now, if I'm going to multiply this in the frequency domain by the low pass filter, then the low pass filter is between minus 200 and plus 200. So it's going to cut everything that is above 210. So what's gonna let go through are frequencies that survive are the 0, the 70 pi, the 140 pi, and the negative also correspondent frequencies. So for this reason, all these 5 frequencies are gonna survive, and this is what's gonna go through. This is the output. Now, here I assumed the way I solved, I assumed that the AKs are 1. So here it should be 2 pi. For example, here it should be 2 pi A0, 2 pi A1. So this is why you have these kind of, these coefficients here, which is the magnitude at each frequency. So it's basically telling you the energy of the signal at each frequency. Okay? So this kind of highlight this idea of, I think the main takeaway here is that how convolution work, especially in terms of filtering, in terms of the low pass filter that only lets frequencies in a certain interval go through. And now in the next few slides, I'm going to talk about other kinds of filters. So you saw a low pass filter. We can also talk about a high pass filter. Let's say this one. So the high pass filter lets frequencies greater than B go through. So again, high pass in the sense that you may say, oh, what is B? Should be anything. As long as it lets frequencies greater than a certain threshold go through, then it is a high pass filter. Now for a low pass filter here, or a band pass filter, it lets frequencies in a certain interval go through. So here it lets frequencies between B1 and B2 go through. And here the spectrum is symmetric with respect to the y-axis, because we're assuming that the filter is a real filter, this is what's done in practice. So, and real signals have a conjugate symmetric spectrum. Now, how does the high pass filter impulse response looks like? So let's try to derive them from low pass filter. So we know that the low pass filter that lets frequencies between minus B and plus B pass looks like this. So if I do 1 minus this filter here, so let's take this 1. So if I do 1 minus the H of a low pass filter, I'm gonna get the following. So I'm gonna get basically what I want. So I'm gonna get this thing here, which is the high pass filter. So this is why when I do the inverse Fourier transform, or CTFT, the inverse CTFT of 1 is delta t, and the inverse of the Fourier transform of the low pass filter is sine bt divided by pi t. So this is how you get the impulse response of a high pass filter should look like. Now for the low pass filter that lets frequencies between B1 and B2 go through, so I can subtract in the frequency domain. You can think of it as the subtraction of 2 low pass filter in the following sense. So let's suppose I have, this is between minus B1 and B2, right? So, and then if you take minus minus B1 and B1, and this is minus B2 and B2. Now if you subtract these things, you're gonna get this one. Right, maybe so I switched B1 and B2 here, but it doesn't matter. So it's gonna be equal to the low pass filter, the difference between two low pass filters, and this is how you get the impulse response of a band pass filter. So here there are two typos. Again, I'm gonna fix. So this is band pass, and this is a function of t. So we have referred to these filters as ideal filters. The reason is that these LTI systems are non-causal. If you look at the sinc function, for example, the sinc function, even if you give an input at t equal to 0, you're gonna get an input for t less than 0. So these systems are non-causal, and therefore we cannot realize them in real world. You cannot have an output before the input. So what we try to do is to approximate these filter and to build filter that approximate these responses. So you're never gonna get in real life a filter that in the frequency domain, a low pass filter that looks like a box function. So maybe you'll get something that approximates it, and maybe let me draw it in green. So maybe that looks something like this, and so maybe here it kind of tries to minimize the effect of the high frequencies and keep the low frequencies. And there's a whole course, and you're gonna take in DSP a whole chapter on filter design, and some of the labs are also going to be on filter design. Now, the last topic I want to talk about in this lecture is the magnitude and phase of an LTI system, or of the output of an LTI system. So here, we know from the convolution property that the output of an LTI system, y of j omega, is equal to x of j omega times h of j omega. So here, this is another typo, right? So, which means that if you write it in the polar coordinates, if you will, so this is the magnitude of x times the magnitude of h times ej, the phase of x plus the phase of h. So for this reason, to represent the output, or to get to magnitude of the output of an LTI system, so the magnitude of the output is the magnitude of the input times the magnitude of the transfer function of the frequency response, and the phase is equal of the output is the phase of the input plus the phase of the frequency response. As a quick example, so suppose x of t is e minus 2t u of t is the input to an LTI system with h of t equal to e minus t u of t. Find the magnitude and phase of the output. And here it's easy by applying the previous formulas. The magnitude is the product of the magnitudes, and the phase is the sum of the phases. And this is what this slide does. So the x of j omega, the CTFT of the input is 1 over 2 plus j, and if you multiply by 2 minus j omega and times 2 plus j omega, you will get this formula here. And now if you find the phase, or if you find the magnitude, is going to be equal 1 divided by square root of 4 plus omega squared. So you can get this immediately by noticing that the magnitude of xj omega is 1 over the magnitude of 2 plus j omega, and this is how you get this one. And the phase is minus arctangent omega by 2. And same thing here, you can get the magnitude of h of j omega and the phase, and then you can apply the property that the magnitude is the product here, and the phase is the sum of the phases.